Today, we'll dive into two fascinating case studies: how AI differentiates between cats and dogs, and how it analyzes the properties of graphene using microscopic images. Let's embark on this journey to understand the differences between these two methods and how they showcase the power of AI. Let's start with a seemingly simple question. How does AI tell the difference between a cat and a dog? While it might sound straightforward, the process involves complex algorithms and sophisticated models. We use convolutional neural networks, or CNNs, to accomplish this task. CNNs are designed to process and analyze visual data. They consist of multiple layers, each responsible for extracting different features from the images. Here's how it works. First, we collect thousands of labeled images of cats and dogs. These images are crucial for training the neural network. Next, we preprocess the images by resizing and normalizing them. This ensures that the data is uniform and ready for analysis. The convolutional layers act as filters, scanning the images to detect basic features like edges and textures. These layers capture the essential details that distinguish cats from dogs. Pooling layers reduce the dimensionality of the data, making the computation more efficient while retaining important features. Finally, the fully connected layers combine the extracted features and make the final prediction whether the image is of a cat or a dog. Now, let's switch gears and explore how AI analyzes the properties of graphene using microscopic images. For this, we employ graph neural networks, or GNNs. Unlike CNNs, GNNs are designed to process graph-structured data. First, we represent the microscopic images of graphene as graphs. In these graphs, nodes represent the carbon atoms. Edges represent the bonds between the atoms. Just like in our previous example, we start by collecting and labeling data. This time, we're gathering information about the physical and chemical properties of graphene samples. We preprocess the graph data to ensure consistency and accuracy, cleaning any noise and normalizing the data. Next, we build and train our GNN model. GNNs consist of layers that aggregate information from neighboring nodes and edges, capturing the complex interactions within the graph. We train the GNN using labeled graph data. During training, the model learns to recognize patterns that correspond to specific properties of graphene. The GNN extracts features from the graph, such as the type of bonds and the arrangement of atoms. These features are crucial for predicting the properties of graphene. Once trained, the GNN can analyze new microscopic images of graphene and predict its properties based on the learned patterns. While both methods using CNNs to differentiate between cats and dogs, and using GNNs to analyze graphene properties leverage the power of AI, they serve different purposes and operate on different types of data. CNNs are specialized for image recognition tasks, processing pixel data to identify and classify visual patterns. GNNs are tailored for graph-structured data, analyzing the relationships and interactions within complex structures. AI's ability to process and analyze diverse types of data, whether it's images of cats and dogs or microscopic structures of graphene, demonstrates its versatility and potential. By leveraging specialized neural networks, we can unlock new insights and applications across various fields. If you enjoyed this video and want to learn more about the wonders of AI, be sure to hit that subscribe button and give us a thumbs up. Thanks for watching, and we'll see you in the next video.